Here's 2019 question 2. This looks like Riemann sum table problem along with velocity. Sorry, particle motion. So it's a little bit of both. This is probably what you may see on this year's modified AP exam. Okay? So just keep that in mind. Here we go. Justify why there must be at least one time t from 0.3 to 2.8. Notice how 0.3 and 2.8 are right here. Justify why there must be at least one time at which the acceleration is equal to 0, aka the derivative. Okay? So right away, the way that they phrase this, why there must be at least one time, or is it possible for this to happen, or does there exist a c? All those types of phrasing refer to either IVT or MVT right away. Okay? Now, because I'm given v of t and they're asking for the derivative, the only thing that involves derivatives are MVT here. Okay? Now, MVT only works if the function is continuous on a closed interval and differentiable on an open interval. So they do mention that the function is differentiable here. So we know that by default, if d, then c, the function will be continuous. So we know MVT theorem applies, but we're looking for specifically 0. Okay, we're looking for where the tangent line or the derivative will come out to 0 here. So we have to do one more piece of evidence here. We actually have to check the average rate of change. So taking a look at this here, is it possible to pick 2 points in between 0.3 and 2.8 where the slope will come out to 0? So right away I noticed that I should probably use 0.3 and 2.8 because they both have values of 55. So when I find the average rate of change there, it would look like this, which comes out to 0. And since the function is continuous and differentiable, so what you guys just found was you found out that the average rate of change or the slope of the secant line is 0. So now we're guaranteed a moment in between where the derivative will have the same slope as well. And that's it. Okay, so by MVT, since the function is continuous and differentiable, and we showed that the average rate of change came out to 0, that guarantees some value in between 0.3 and 2.8 such that the derivative is 0. Okay, so there you have it. Okay, part B. They want us to use a trapezoidal sum using the interval 0.0 to 0.3 to 1.7 to 2.8. Notice how they didn't go all the way through the entire table. Very tricky. Now here they're just asking for the integral and not the average. So watch out for that, okay? So here we go. We're going to have 1/2 times the horizontal distance times the sum of the two bases. Okay? Plus 1/2 times the horizontal distance. Sorry, that's not 0.4. That's 1.4. Times 55 plus negative 29. And the last one plus 1/2 times the horizontal distance, which should be 1.1, times negative 29 plus 55. Okay? This right here is enough for equal is equal. You should get 2 points there. Should we get 2 points? Actually, no, they only provide 1 point here. Okay? All right, let's keep going. Here's part C. A second particle Q, so they introduce a new particle here, moves along the x-axis, so that its velocity is this equation here. Find the time interval during which the velocity of the particle is at least 60 meters per hour. Find the distance traveled by particle Q during the interval when the velocity is at least 60 meters per hour. So there's two parts to this question, okay? You have this particle Q. Okay? They give us its velocity. And they're telling you, well, from when to when will the particle be at least 60 meters per hour, okay? So what you do is on your calculator, you would graph this. Let's call this y1. Okay. And what I would do is I would probably graph y2 as 60. Okay. And you're going to graph it from 0 to 4. All right. From 0 to 4. So once you do that, you're going to look at the graph. Okay. So it's looking like, I don't have the exact picture on me, but there's going to be two intersection points. You're going to have some curve and then some horizontal line that cuts through the curve twice. Okay? It intersects the curve at 1.866 and at 3.519. Okay? But you notice, and I'm not drawing the exact picture here, you guys. You notice that at 1.866 and 3.519, the curve is above in between, implying that the velocity is going to be larger than 60. So the time interval is going to be everywhere in between. So everywhere in between 1.866 and 3.519, you're going to get your time interval where the velocity is at least 60 meters per hour, okay? So that's that. Here's the second part to this problem. We want to find the distance traveled during the time when it was at least 60 meters per hour. So do we know the time interval? We do. It's 1.866 to 3.519. How do we find the distance? Okay, so total distance, if you guys remember, you have to integrate the velocity of q, but you have to integrate the absolute value of velocity of q from 1.866 to 3.519. Okay, that's a quick plug and chug. You should get about 106-ish. They don't ask for units, so you should be fine. But if they were to ask for units, what would you use, right? What unit would you use for distance? In this case, it would just be meters. Okay? Here's the last one. At time t equals 0, the particle q is at position x equals negative 90. Use the result from part B and the function v of q from part C. Approximate the distance between the two particles. Okay, so this is a very layered problem, okay? So let me paint a picture for you guys. So ultimately, we want the distance between particles P and Q at time t equals 2.8. So here's what you guys have to figure out. At t equals 2.8, particle P is somewhere, and particle Q is somewhere. If we can find out where they are, we can find their distance. Okay? So, before we actually find the distance, let's find out where P and Q are first. Okay? So, with particle P, do they give us any fact about where they are? Right? So, notice how it says that we want to use the particle, the part B here. Now, let's go back to part B. We just integrated v of p, okay, the velocity of particle p. When you integrate v, you go back to position, okay? So let me write this one out here. So for p, if we integrate from 0 to 2.8 of the velocity of p of t, which is our trapezoidal approximation, okay? That just gives us our accumulation. We actually have to consider where we started, but they actually tell you right here, I'll highlight it, particle P is at the origin. So I'll just put 0 plus here just for pattern's sake, okay? We approximated this, okay? I didn't go all the way through with our red text here, but I'll just refer to the scoring guidelines. So in part B, if you crank this one all out, you should get 40.75. This is where particle P is at 2.8. So we know particle P is at 40.75. I don't know if Q is to the left or to the right yet. This is just a general picture, okay? Okay, now for Q. So we have to do the same thing. We have to integrate the velocity of Q from 0 to 2.8. But where is Q at t equals 0? So let's read this carefully. It's right here in part D. At t equals 0, particle Q is at negative 90. So you have to consider that Q started at this value. Okay? So this could be done on a calculator here. You would just integrate via sub Q of t from 0 to 2.8, add the negative 90. Let me look at the scoring guidelines here. This comes out to about 45.938 if you round it. Okay, so particle Q is actually at 45.938. So what do we just find? At 2.8, t equals 2.8, we now know where they are. But that's not what they're asking for, okay? They're asking, well, how far are they from each other? What's the distance? So what do? We just subtract the two. 45.938 minus 40.75. That should give you about 5.188 or 187, depending on what you did, okay? No need for units, so I'll just leave it at that. And that's it.